Good evening to all of you. Today's session is on thermal remote sensing. The thermal remote sensing is mainly carried in the thermal region of the electromagnetic spectrum. So, we are going to explore about the properties of the electromagnetic wave and the imaging in thermal region of the electromagnetic spectrum. Thermal infrared energy is emitted from all objects that have a temperature greater than absolute zero. Therefore, all the features we encounter in landscape on a typical day emit thermal infrared electromagnetic radiation. Humans sense thermal energy primarily through the sense of touch. Our eyes cannot detect differences in the thermal infrared energy because they are primarily sensitive to short wavelength visible range from zero point 0.4 micrometer to zero point 0.7 micrometer. Our eyes are not sensitive to the reflective infrared that is covered under zero point 0.7 to 3.0 micrometer, zero point 0.7 to 3 micrometer, or thermal infrared energy that is covered under 3 to 14 micrometer range of the electromagnetic spectrum. Fortunately, engineers have developed detectors that are sensitive to thermal infrared radiation. These thermal infrared sensors allow humans to sense a previously invisible world of information as they monitor the thermal characteristics of the landscape. If you will see thermal remote sensing, so thermal remote sensing for Earth observation is done for the Earth surface, and if you will see in any small area, it might be possible that in a small area it might be possible that there will be different kind of objects which will emit the thermal radiation. So here you can see, like there in a small area, the vegetation cover is there, particularly when we are able to see these trees. So group of trees are there, and the grasses are there, bare soil is there, road surface is also there, and built up area is also there. So they all are going to contribute in the thermal emission, and the energy which will be emitted by these objects will be sensed by the satellite. Sensor will be placed in the satellite, and that is going to sense the electromagnetic energy radiated or emitted by the different objects of the earth surface, and finally that will be converted into image, and finally imaging will be done for the earth surface. Now this thermal image will have the characteristic about the thermal emission of the different kind of objects, which will be different for the different kind of objects. Like the thermal emission for a vegetation will have the different behavior than the urban buildings, and similarly it will have the different behavior than the bare soil. So based on that, one will be able to discriminate the different geophysical and the biophysical parameters of the earth surface. This is an image which is captured in the multispectral data set. So here for the this image captured by the Copernicus Sentinel-2 mission on 30th September shows the flow of the lava from the volcano erupting on the Spanish island of La Palma. So here you can easily see that this is like a combination of blue band, red band, and the reflected infrared band. So this two color composite image is generated, and one can easily see that this information, the lava flow is having very high reflectivity in the reflected infrared, so that could be detected. So but not only this, suppose the area is covered by the dust or cloud, so or the thick cloud cover, so the temperature information could be retrieved. Like here we can have the information of the lava flow, and from visualization one can say that temperature is very high, but how much temperature this one, so or what is the temperature of the surrounding area, so that could be detected with the help of, that could be retrieved with the help of the thermal data set. So now this is another example in which we are going to see the two different kind of sensors which have been used here to detect the lava flow of volcanic eruption of Hawaii Island. So Kilwa Mountain of Hawaii Island that had started erupting on 3rd May 2018, So now the left side image is the image, false color image, which is generated with the help of the SAR data set. Now here you can see that the lava flow was easily detected in the SAR data set. The lava flow direction is easily detected. Now when the information and here you can see that for the same area, with the help of the optical multispectral data sets of Sentinel-2, two bands of Sentinel-2 and one band number 10 thermal band of Landsat 8. This was used to generate the false color composition. Now here you are able to clearly see, detect the temperature information. Now for the detailed information of this work, this analysis, one can go through the literature which I have cited here. Now these are the two images of a volcano. So the left side image is the nighttime thermal image, and the right side image is the is again the ASTA data set for the 6 January 2002, but this is the optical multispectral data set. Now in the optical multispectral data set, we are able to clearly visualize the information of different kind of objects based on the color information, and some other information could also be visualized based on the structural properties of the object. So since we are knowing that optical multispectral data set is mainly sensitive to the top color information of the object, because mainly a reflected portion of the electromagnetic wave is used to do the imaging. So here this will have the sensitivity for uh, uh, the top color of the surface. Now when we are coming to the thermal data set, so in thermal data set we are able to see, like, this is only one band of the data set. This is only one band, and in this band when the color information is provided, so according to the values, so here what we are going to see, we are going to see a very bright patch at the center of the volcano. So because from the shape it is clear that this is the volcanic crater. So inside the crater we are able to see the very bright patch. It means that very bright patch is representing that very high thermal emission is there, because this is a thermal data set. So all the objects which are going to have very high thermal emission, they are going to appear as very bright features. So here this is appearing very bright. It means that there is some kind of volcanic activity going on. It means that this is if the volcano will be completely dead, so this portion is not going to appear very bright, or this is not going to show very high temperature. This is showing very high temperature, high thermal emission. It means that some volcanic activity is going on. Now one more example we are going to see, like what are the advantages of thermal remote sensing. So in the previous example we have seen that, like from optical multispectral data set, if the volcanic eruption is not completely active and it was not erupted, then it will be difficult from optical multispectral data set to say about any volcanic activity inside the crater of the volcano. But if you will have the thermal data set, so by increase or decrease in the temperature inside the volcanic crater, one will be able to clearly understand uh, the the heat information or the volcanic activity, type of volcanic activity within the crater. Now there are several other advantages. One example, this is I am going to show you regarding the white rock. So white rock is the unofficial name for this unusual landform, which was first observed during the Mariner 9 mission in the early 1970s. A later analysis of additional data sets would show that white rock is neither white nor dense. So here, the for the analysis, we selected the two data sets. One is optical multispectral data set, and here you can see that this is the nighttime data set. So here you can see that in this data set, the earlier in the optical multispectral data set, this was imaged as very white, so that name was given white rock. But when the thermal data set analysis was done, so if it will be a rock, so in the night time also this will show the high thermal emission. But here, if you will see, like the rim of the surface, this is going to show you very bright temperature, very high thermal emission. But those kind of emission is not retrieved from the white rock. So it means that indicates that this particular landform is not very dense, and this is not as rocky or not as bedrock. So this kind of analysis will help in the planetary studies also. Now another example is given for like urban area. So here you can see that the yellow and red areas in this imagery are hot and generally correspond with roads and buildings. Blue and green area are cool and indicate water and vegetation. The bright red areas in this image are about 65 degrees centigrade, which you will convert in the Fahrenheit, then it will be approximately 149 degree Fahrenheit. Dark green and blue areas are around 25 degrees centigrade, that will be around 77 degree Fahrenheit. The solid blue swatch of color flowing down the left side is the Mississippi River. So here you can see that for water and vegetation, the temperature is low or very low, and this is daytime imagery. And in the daytime imagery, approximately 65 degree temperature is there from the urban area. And here the in the left side image, if you will see, this is the true color composite image of the same area. So in the true color composite, what you are going to see, that all the urban buildings, they are highlighted, they are showing very high temperature, that is represented either in yellow color or red color, and the vegetation covered area is either coming in green color or blue color. So here you can easily see the difference in the temperature. Now we are going to talk about the fundamental properties of the electromagnetic radiation. So the three basic ways in which energy can be transferred, uh, these are conduction, convection, and the radiation. Conduction occurs when one body or molecule or atom of the body transfers its kinetic energy to another by colliding with it. This is how a pan is heated on a stove. In convection, the kinetic energy of bodies is transferred from one place to another by physically moving the objects. An example is the convectional heating of air in the atmosphere in the early afternoon. The transfer of energy by electromagnetic radiation is of primarily interest to remote sensing because it is the only form of energy transfer that can take place in a vacuum, such as the region between the sun and the earth. Because here, when we are talking about the thermal remote sensing, so in the thermal remote sensing, when the energy will be transmitted from the sun to the earth surface, so there is a vacuum, there is no medium. So here the properties of radiation, or the way of radiation is used to explain the concept of propagation or transfer of energy from one place to another place. These examples are given, like in the case of conduction. Here you can see when the pan is directly in the contact with the burner, and finally the heat is transferred. In the convection, so here you can see that in the convection, the air particles, the hot air particles are going up, and finally heat is transferred. In the case of radiation, electromagnetic waves, they are carrying energy particles, and finally, or you can say the photon particles, and these particles are carried by electromagnetic wave, and they will be transferred towards the earth surface. Now when we are talking about the thermal infrared spectrum, so when we are talking about infrared spectrum, so infrared spectrum covers the two types of infrared. One is the reflected infrared, Another is the emitted infrared. So reflected infrared is having the range from 0.7 micrometer to 3 micrometer, and the reflected and the emitted infrared, that is the thermal infrared, that will be covered under 3 to 14 micrometer range of the electromagnetic spectrum. Now, when you will see the atmospheric windows in the electromagnetic spectrum, so we are mainly talking about the thermal infrared. So here, if you will see in the 3 to 5 micrometer, in between 4 to 5 micrometer, there is absorption due to the CO2. And again, if you will see the range, which is 3 to 14 micrometer for thermal infrared, so the entire range is not used for the remote sensing purpose, because there is one absorption band. So 5 to 8 micrometer is the absorption band. Here you can see that all the energy between 5 to 8 micrometer will be completely absorbed by the atmospheric water vapor. So this particular band, 5 micrometer to 8 micrometer, is not used in the imaging purpose. So that 8 to 14 micrometer is used in the remote sensing for the for the imaging purpose. Uh, Thermal infrared radiation refers to the electromagnetic waves with a wavelength of between 3 and 20 micrometers. Most remote sensing applications make use of 3 to 5 and 8 to 14 micrometer due to the absorption bands of 5 to 8 micrometer. The main difference between thermal infrared and near infrared is that thermal infrared is emitted energy, whereas the near infrared is a reflected energy, similar to visible light. So that here you can see that most of the optical multispectral sensors, they will have one band, at least one band in the near infrared region, because the similar concept is used to do the imaging in the near infrared. Now, when we are talking about the thermal remote sensing, so we should understand about the source of the energy, because here we are talking about the emitted energy. So this energy is also known as the kinetic energy, and the generated heat is also known as the kinetic heat. The energy of particles of matter in random motion is called kinetic heat, and this is also referred to as internal, real, true heat, or kinetic heat. All objects having a temperature above absolute zero, that is 0 degree Kelvin, or you can say that minus 273.16 degrees centigrade, exhibit this random motion. Means all the objects above absolute zero will radiate electromagnetic energy, because when the particles of the objects, they will collide, so they will change their energy state, and when they will change their energy state, they will emit the electromagnetic radiation, and that electromagnetic radiation will be converted in the form of energy, and finally that will be the thermal energy, or when it will be converted to heat, then that will be thermal heat. The amount of heat can be measured in calories. We can measure the true kinetic temperature, that is also represented by T kinetic, or concentration of this heat, using a thermometer. We perform this in situ temperature measurement when we are ill, because most of us have already used thermometer to measure the temperature. We can also measure the true kinetic internal temperature of soil or water by physically touching them with a thermometer. So with the help of the thermometer, we can easily measure the true temperature of any object. Fortunately for us, an object's internal kinetic heat is also converted to the radiant energy. The electromagnetic radiation exiting an object is called radiant flux and is measured in watts. The concentration of the amount of radiant flux exiting an object is its radiant temperature. There is usually a high positive correlation between the true kinetic temperature and the radiant temperature. So radiant temperature is represented by T radiant. So with the help of radiometers, one can easily measure the radiant temperature, and when the radiant temperature is measured, we expect that the kinetic temperature or true temperature could be easily measured. But unfortunately, the relation is not perfect because the internal temperature is proportional to the kinetic temperature, but emissivity plays an important role. So emissivity is the thermal property which is going to change the values of the radiant temperature. Like if we are talking about the radiant temperature and kinetic temperature, so if the emissivity, if emissivity will not be there, so the object, the heat which will be radiated by the object will be directly captured by the sensor, and finally at that time kinetic temperature will be exactly equal to the radiant temperature. But here emissivity of the surface is playing very important role, so that kinetic temperature is not equal to the radiant temperature. So mainly the thermal property of any object or thermal emission is mainly governed by the two factors, and these are the internal temperature, or we can say that kinetic temperature, and the emissivity of the surface. Now here we are going to talk about some basic laws of which are used in the thermal remote sensing. So first we are going to talk about the Planck's law of blackbody radiation. The Planck's blackbody radiation law describes the electromagnetic radiation emitted from a blackbody at a certain wavelength as a function of its absolute temperature. So here we can see that the spectral radiant excitance will be equal to 2 pi hc square divided by lambda to the power 5 e to the power hc divided by lambda kt minus 1. So here h is Planck's constant, c is speed of light, k is Boltzmann constant, t is absolute temperature, and lambda is the wavelength. Now when we are talking about the black body curve, so the total energy black body radiates and the wavelength of maximum emittance depend on the temperature of the black body and can be described by the Stephen Boltzmann law and Wind's displacement law. Black body radiation curves at selected temperatures. Uh, the laws of the Planck's Stephen Boltzmann and Wind are depicted in the figure. The blue bar indicates the visible region, because here this is representing 0.4 micrometer to 0.7 micrometer, and Wind's displacement law is represented by the dotted line, and the shaded area under the 300 Kelvin is representing the Stephen Boltzmann law. So here we are going to talk about the Wind's displacement law. So the relationship between the true temperature of a black body in degree Kelvin and its peak spectral excitance or dominant wavelength is described by Wind's displacement law. So dominant wavelength, that is represented by lambda max, is equals to k divided by t, where k is constant, and this is equals to 2898 micrometer degree Kelvin. So when the temperature in degree Kelvin of any object could be measured, so with the help of the measured temperature, one will be able to find out the dominant wavelength. So this could be used in the imaging also. Like here, for an example, here you can see that the average temperature of Earth is around 300 degree Kelvin, that will coming 80 degree Fahrenheit. So when you will try to calculate the dominant wavelength from the Earth's surface, so this will be coming 2898 divided by 300 degree Kelvin, so that will be approximately 9.67 micrometer. It means that for doing the imaging of the Earth's surface, 9.67 micrometer is the most suitable, because the this wavelength range is equal to the average thermal emission temperature, that is 300 degree Kelvin. Similarly, if we are talking about the forest fire, So the dominant wavelength provides valuable information about which part of the thermal spectrum we might want to sense it. So here example is given. If you are looking for 800-degree Kelvin forest fires that have a dominant wavelength of approximately 3.62 micrometer, then the most appropriate remote sensing system might be a 3 to 5 micrometer thermal infrared detector. So according to one's application, one will be able to find out the most suitable wavelength range for their particular application of thermal remote sensing. If we are interested in soil, water, and rock with ambient temperature on the Earth's surface of 300-degree Kelvin and a dominant wavelength of 9.66 micrometer, then a thermal infrared detector operating in the 8 to 14 micrometer region might be the most appropriate. So that here you can see that most of the Earth observation satellites in the thermal remote sensing, they are designed to acquire the data set in the longer wavelength ranges of the thermal infrared. Now another law is the Stephen Boltzmann law, that is derived by integrating the Planck's function with respect to wavelength. So this tells about the energy or the radiant flux and the temperature. So this is saying that energy is proportional to the fourth power of the temperature, and when the proportionality constant will be removed, so this is removed by placing the by placing the Stephen Boltzmann constant, that is represented by sigma. So E will be equals to sigma T to the power 4. So, if the temperature is known, so by putting these values by multiplying the fourth power of the temperature with the Boltzmann constant, one will be able to calculate the energy. Now, the kinetic temperature, as we have already talked, this is the internal temperature that is generated with the random molecular motion, and emissivity of the surface is going to play a very important role when we are measuring the radiant temperature. So when we are going to compare the kinetic temperature and the radiant temperature, so those will not be equal, and we can calculate the radiant temperature when the kinetic temperature is known, or when the kinetic when the radiant temperature is known, then the kinetic temperature could also be calculated. So a radiant temperature will be proportional to the kinetic temperature, but this will be weighted by the emissivity. It means that here, if you will see the formula, T radiant will be equals to 1/4 power of the emissivity and multiplied by the kinetic temperature. It means that the radiant temperature of the surface will be equal to will always be less than the kinetic temperature, because the radiant temperature will be equal to the kinetic temperature, or you can say the temperature which is sensed by the sensor will be equal to the internal temperature of the object, if emissivity will be equal to 1, and the emissivity will be equal to 1 only for black body. Emissivity is going to vary between 0 to 1. So all the objects, all the gray objects, they will have the emissivity in between 0 to 1. The black body is an ideal object or ideal surface which will have the emissivity 1. So only for the black body, radiant temperature will be equal to the kinetic temperature, and for all the other objects, the radiant temperature will be less than the kinetic temperature, because the emissivity will be less than 1. Now, the world is not composed of radiating black bodies, because here we have seen that the emissivity of the black body will be 1. Rather, it is composed of the selectively radiant bodies such as the rock, soil, and water that emit only a fraction of the energy emitted from a black body at the same temperature. Emissivity epsilon is the ratio between the radiant flux exiting a real world selective radiating body and a black body at the same temperature. So here you can see that emissivity is given as the ratio between a ratio of Fr and Fv, and where Fb is uh, representing the radiant flux of the black body, and Fr is representing the radiant flux of the real world object. Now, as we have seen that emissivity will be in between 0 to 1. The object which will be having no emission, that will have the emissivity 0, but all the objects on in the world, they will have the emissivity in between 0 to 1. Some objects like distilled water have emissivities close to 1, that will be 0.99, and some objects they will have very less emissivity, like in the case of the polished aluminum as well as the stainless steel. For polished aluminum, the emissivity is 0.08, and the stainless steel, this is 0.16. So the metallic objects, they will have the very less emissivity, and generally emissivity is also going to vary according to the wavelength ranges. So generally the distilled water, this will have the 0.99 emissivity in 8 to 14 micrometer wavelength range. Now there are several parameters which are going to affect the emissivity. Two rocks lying next to one another on the ground could have the same true kinetic temperature but have different apparent temperatures when sensed by a thermal radiometer, simply because their emissivities are different. The emissivity of an object may be influenced by a number of factors, and those factors are listed here. Color. So darker color objects, they will have the better capability to absorb the thermal radiation. So they will absorb it, and finally they are the good emitters also. So in comparison to the light color objects, so the darker the color, higher will be the emissivity. And the second factor is surface roughness. The greater the surface roughness of an object related to the size of the incident wavelength, the greater the surface area of the object and potential for absorption and re-emission of the energy. It means that rough surface will have the higher emissivity in comparison to the smooth surfaces. Now the moisture content, if the moisture content will be more, the greater will be the absorption capability, and finally those objects are going to emit the thermal radiation. So those are good emitters. So wet soil particles have a high sensitivity similar to water. Now field of view of the sensor, now these are the sensor parameters, like field of view, the emissivity of a single leaf measured with very high resolution thermal radiometer will have different emissivity than an entire tree crown viewed using a coarse spatial resolution radiometer. So definitely the field of view is also going to take very important role, because emissivity is going to change, because in a small area for a single leaf, that will be contributed mainly due to the properties of the tree leaf, but when the entire area or entire tree will be captured, so the thermal emissivity will be contributed by the branches also. And if we are talking about the resolution cell of 100-meter or 60-meter, then there are several other features also, like ground, water, urban area, or any rock. So they all are going to contribute in thermal emission. So at that time, the emissivity will be different. Now, wavelength is also going to play important role. The emissivity of an object is generally considered to be wavelength dependent. For example, while the emissivity of an object is often considered to be constant throughout the 8 to 14 micrometer region, its emissivity in the 3 to 5 micrometer region may be different. Viewing angle of the camera, so emissivity is also going to depend on the viewing angle of the camera. So, when we are talking about the thermal properties and emissivity of the object, so that is described based on the Kirchhoff's law of radiation also. So we are going to understand something related to Kirchhoff's law. So incoming radiation, that will be distributed in three parts. So one part will be reflected, another some portion will be absorbed, and some portion will be the transmitted. So here we are going to see that if the we are going to talk about the reflectance, absorbance, and transmittance. So it means that the total incoming radiation will be the sum of the reflected radiation, absorbed radiation, and the transmitted radiation. Now, reflectance will be the capability of the sensor to reflect it. It means that the reflected radiation, when the reflected radiation will be divided by the incoming radiation, then that will be become the reflectance. Similarly, when the absorbed portion of the energy will be divided by the incoming radiation, so that will be known as the absorbance. And similarly, the transmittance, that is capability of the surface to transmit the electromagnetic energy or the incoming radiation. So when the transmitted radiation will be divided by the incoming radiation, so that will become the transmittance. Now it means that the sum of absorbance, reflectance, and transmittance will be equal to 1. So here we can see that sum of transmittance plus reflectance plus absorbance is equal to 1. So here we can see how the absorbance and reflectance and the transmittance were derived. So tau is representing transmittance, rho is representing reflectance, and alpha is representing absorbance. Now most of the objects on the Earth's surface, they are opaque in nature. They are not going to allow electromagnetic waves to transmit through it or thermal radiation to transmit through it. So if they are opaque, it means that their transmittance will be 0, and the absorbance will be equal to the emissivity. So now when you are going to reflect the absorbance with emissivity, so what you are going to get, emissivity plus reflectance will be equal to 1. It means that when you will see this relation, it means that when emissivity will increase, then the reflectivity will decrease. When reflectivity will increase, then emissivity will decrease, because the sum of emissivity and reflectivity is equal to 1. So now here one can see that since the metallic structure, all the metallic objects, they are very good reflector. It means that they are the poor emitters. They are poor absorber and the poor emitters. It means that all the objects which are good reflector, they are poor emitters. Now if you will see the rough surfaces, dark color objects, they are poor reflectors. It means that they will have high emissivity. It means that good emitters are poor reflectors. So these concepts are used when we are doing the interpretation of the image based on the thermal properties of the objects. Now here we have seen there are different sensor and object parameter. We are going to now talk about the thermal properties of the terrain. So water, rocks, soil, vegetation, the atmosphere, and human tissues, they all have the ability to conduct heat directly through them. Some materials respond to changes in temperature more rapidly or slowly than others. So there mainly we are going to see the three properties: thermal conductivity, thermal capacity, and thermal inertia. So thermal capacity, when you will see, generally this is represented by C. Thermal capacity is the ability of material to store heat. It is measured as the number of calories required to raise a gram of material 1 degree centigrade. Water has the highest thermal capacity, that is equal to 1. It stores heat very well relative to all the other materials. Now the second thermal property of the terrain is the thermal conductivity. This is represented by generally K. Thermal conductivity is the rate that heat will pass through a material and is measured as the number of calories that will pass through a centimeter cube of material in 1 second when two opposite phases are maintained at 1 degree centigrade difference in temperature. The conductivity of a material is variable due to soil moisture and particle size. Many rocks and soils are extremely poor conductors of heat. Now the third property is the thermal inertia, which is represented by P. Thermal inertia is a measurement of the thermal response of a material to temperature changes and is measured in calories per square centimeter per second square root degree Celsius. Thermal inertia is computed using the equation. Thermal inertia is multiplication of K multiplied by P multiplied by C, where K is the thermal conductivity, P, or this is basically rho, is the density, and C is the thermal capacity. So in the thermal remote sensing, sometimes we are measuring the thermal inertia also to know the thermal properties of the terrain or thermal properties of the object. So generally, when we are talking about the Earth surface, so when the target is pure, then it is not very difficult. By doing the field measurement, one can measure the thermal inertia, because thermal inertia is a measure of resistance of a material to temperature changes. So, but here when we are talking in the remote sensing, so one resolution cell will have the different kind of objects. So there we are going to measure the apparent thermal inertia. So to measure apparent thermal inertia, we are going to measure the difference between the maximum and the minimum temperature of a diurnal solar cycle. So here you can see that for every surface, like here for one surface, we are measuring the change in the temperature between the maximum difference of the maximum and minimum temperature. By measuring this temperature, one will be able to measure the apparent thermal inertia. So apparent thermal inertia, this is measured with the help of the formula. This is shown here, 1 minus A divided by delta T, where A is the albedo that is measured, that is basically reflectance, which is measured with the help of the visible bands. So when and delta T will be measured from the thermal band. So when these parameters will be measured, one will be able to measure the apparent thermal inertia. Now we are going to see the radiant temperature of 5 surface cover type during a 24-hour thermal cycle. So here you can see that in this diagram, in the graphical representation, you can see that the metallic objects, so they will have a very less variation in the thermal emission, because their thermal emission is very low. Here you can see that the radiant temperature detected by the sensor, so this is not very high, particularly when we are talking about the thermal band. Not we are not talking about the optical multispectral band, because in optical multispectral band, reflectivity value will be very high, so these will metallic surfaces are going to appear very bright. But here in the thermal, they will not appear very bright, because their emissivity will be low, and the sensed radiant temperature will also be small. Now for damp terrain, so this will have a similar pattern to the metallic object, but higher radiant temperature in comparison to the metallic objects. Now when we are going to see the rocks and soils, so there is a very high change in the daytime and the night time. Here you can see that approximately at 2 o'clock or 14 o'clock noon, afternoon, the maximum temperature will be sensed by the sensor. The radiant temperature will be maximum, and after that there will be sudden decrease in temperature, and finally in the night time, approximately after 8 o'clock, the temperature will become very low. Now in vegetation, here you can see that the radiant temperature for vegetation and standing water is high, and there is also very less change in the daytime and night time. So it might be possible that in the daytime thermal imageries, the rocks and soil, they will have the very high radiant temperature in comparison to the vegetation and water, but in the night time, the vegetation and standing water will have higher radiant temperature in comparison to all the other features. Now this is image. This is an image of Landsat TM data set. Band number 6, nighttime image was taken for the Great Lakes. So here you can see that the water is appearing very bright, and here you can see that even when the water bodies are connected through channel, so in this channel also water is appearing very bright, and here you can see that the land is appearing dark because less emissivity is there in comparison to not only less emissivity, thermal properties also, like thermal energy, and there are other properties. So it cannot hold the heat for a longer time, so this is appearing dark, and the water can store the heat for the longer time, and it will re-radiate it in the atmosphere. So finally that will be sensed by the sensor, so this is appearing bright. Now here we are going to see the some famous thermal sensor. So here we are going to see the inside 3D. So this is not used for the mainly for the land. This is mainly used for the sea surfaces. So the two thermal infrared bands are there, and it will have the ground resolution approximately of 4 kilometers. So even if it will be used for the ground, then also this could not be used for a small area. This could be used for the uh, global applications, because the resolution is very coarse, either regional or global. So here you can see that TIR1 band is 10.3 to 11.3 micrometer. TIR2 is TIR representing thermal infrared is 11.5 to 12.5 micrometer. So here you can see that resolution, spatial resolution is 4 kilometer. Now another band which I am going to show, this has also been used widely for the land applications. This is Aster thermal infrared band. So in the Aster thermal infrared band, here you can see that there are several bands of the visible range, as well as the infrared range, reflected infrared range, and there are five thermal infrared band, and here you can see that this is covering 8 micrometer to 11.6 micrometer, and this is having a spatial resolution of approximately 90 meter. So when one these Aster thermal infrared bands have been widely used by the scientific community in different applications. Now another is NOVA AVHRR thermal infrared band. This has also been used, but not for the local or not for the small area. This has been used for the regional and the global applications. So thermal infrared, there are two bands, band number 4 and band number 5, with a spatial resolution 1.1 kilometer. And here you can see that the wavelength range is the for band number 4, this is 10.30 to 11.30 micrometer. For band number 5, this is 11.5 to 12.5 micrometer. Now, Landsat series of satellites have also been widely used in the scientific community, as well as by by the researchers and students, because all these data sets are freely available, and the resolution is also very high, and one can get the high resolution of approximately 30-meter resolution of the optical multispectral and thermal data set also. So here you can see that in the Landsat 4 and 5, band number 6, that is of 120-meter spatial resolution, but this is resampled at 30 meters, so that there should not be any mismatch in the pixel size of the optical multispectral bands. So the band number 6 was the band number 6 is working in 10.4 to 12.5 micrometer, and this has been widely used by the scientific community to do the time series analysis of to measure the thermal properties of the terrain, as well as the heat information in the urban area. So this has been widely used. Now another sensor is Landsat 7. So in Landsat 7 also, band number 6 is the thermal band. Band number 1, 2, 3, 4, 5, 7, and 8, these are the multispectral band, as well as the near infrared band. Band number 7 is near infrared. Now And band number 8 is the panchromatic band, that is providing the high spatial resolution of the 15 meter. So band number 6, here you can see that the resolution was higher in comparison to the Landsat 4 and 5. This is 60 meter, and it is resampled at the 30 meter, and again the range is 10.4 micrometer to 12.5 micrometer. Now these are the specifications of the Landsat 8 sensor. So now in the Landsat 8 as well as in the Landsat 9 also, you can see that the Landsat 9 is recently launched. Now in Landsat 8 there are two thermal infrared sensors. Two thermal bands, band number 10 and band number 11. So band number 10 is working in the range 10.6 to 11.19, and band number 11 is working in 11.5 to 12.51 uh, micrometer range of the electromagnetic spectrum. Now I have covered my lecture, and thank you.